Our next speaker is Yiding Feng, who will tell us about bias-variance games. Yiding, the floor is yours.
Yeah, thanks. So hello, everyone. I'm Yiding Feng. I'm a postdoc at Microsoft Research. Today, I'll be happy to talk about my joint work with Ronen from Ariel, who also attends the EC in person here, and Jason and Aleck from Northwestern, and Denis from University of Virginia. So nowadays, there are many applications which use a prediction algorithm, and lots of them try to use a prediction algorithm under competition. And the natural question we want to ask is that, what will be the effect of the competition on the choice of the prediction algorithm? For example, are prediction algorithm optimal in isolation, still optimal under competition? If it is not the case, so which algorithm are better under competition? And let's try to first start with the following toy example, which I hope to motivate our paper. So this is just a toy example, so please forgive me for me to describe it at a high level. Let's say suppose that we have a firm which wants to use a ridge regression to predict the housing prices. Specifically, suppose that we are giving a feature vector of the house, and we want to run the ridge regression to predict the price of this house. And ridge regression basically will try to solve an optimal parameter beta, which will try to minimize the mean square error on a training data set minus a regularization term. So for ridge regression, it will be lambda times the L2 norm of the beta. And here, the parameter lambda will be a parameter which can be controlled by these firms. And it will control this so-called bias-variance trade-off, which I will formally define in the later of the talk. But loosely speaking, so bias and variance will be two components in the prediction error. And it will form a trade-off in the sense that, so if you have a higher lambda, you will suffer a higher bias and a lower variance, and vice versa. And let's assume that the payoff of the firm is some fixed reward, let's say 1, minus the prediction error on a testing data set. Here I draw how the payoff is influenced by choosing this tuning parameter lambda, where I'm using the data source which is from the California housing pricing data set. As you can see, so this payoff will depend on this lambda, and the optimal payoff, in other words, the optimal bias-variance trade-off, is attained for some lambda strictly greater than 0. And so far, we are talking about an example where there is a single firm which we're trying to use a prediction algorithm to predict the housing price in isolation. Now let's assume that there is another firm join the market. And now two firms want to compete using the ridge regression. And let me modify the payoff of the firm. It will still be the fixed reward minus the mean square error on a test data point if this firm has a smaller realized prediction error. And otherwise, if it has a higher realized prediction error, his payoff will be 0. So you can interpret this as follows. Suppose there is a consumer who come to the two firms, and both firms, given the feature vector, will make a prediction about the house. And this particular consumer will pick the firm which has a better realized prediction. And therefore, the winner of the firm will get the payoff as before, and the loser will get payoff 0. And once again, so we can draw this plot, which will be how the payoff change as a tuning parameter lambda. Here are the different curves corresponding to the different lambda which will be picked by the opponent. And as you can see here, the payoff curve is monotone decreasing with respect to the lambda 1 for the firm 1, regardless of what is lambda 2 for the firm 2. And this basically suggests that the bias-variance trade-off at lambda I equals to 0 become a dominant strategy in this particular example. And this shows differences between the prediction algorithm in isolation and under competition. And motivated by this toy example, so in this paper, what we want to try to understand is that, so what will be the bias-variance trade-off under the competition? And to do so, we introduce a model which we call the bias-variance scheme. And the qualitative results is saying that the optimal bias-variance trade-off in isolation may no longer be optimal under competition. And generally speaking, so what we observe is that bias is more harmful than the variance. And we will be more clear about those two takeaway messages in the end of the talk. So, cool. So before I present our model of bias-variance schemes, let me first try to revisit a very classic framework for the statistical decision theory, which will be the starting point of our model. Let's suppose that there is a distribution over a pair of x and fx, where x you can interpret as a feature vector, for example, the feature attribute of a house. And fx, which will be a label, for example, the price of a house. And in this talk, for simplicity, let's assume that the label will be beta times x plus some random noise. And basically a learning algorithm, you can interpret it as it will take a training data set as input and output an estimator, which we denote as f hat d. And we use subscript d to denote that this estimator is computed by the training data set d. And then we can introduce two quantities. The first is a mean square error loss on a given feature x. So basically it will be the differences between the predicted label minus the actual label square. And the rest of our algorithm is basically the expectation of the loss when we take the expectation over the randomness of the training data set. And so we can rewrite this rest into three components. The first one is called bias. The second one is called variance. And the third one is an irreducible error. So basically, by picking different learning algorithms, so what it to do is that it will lead to different value of bias and variance. Yeah, and in the end of the day, lead to different expected rest. And we say that usually there will be a trade-off between the bias and variance in the sense that usually when you have a learning algorithm which has smaller bias, usually you will suffer a larger variance, and vice versa. And therefore, we call there is a bias-variance trade-off. And in this framework, there is a rich class of algorithm, which we call the empirical risk minimization. Specifically, it's try to basically solve the optimal estimator, which will try to minimize the empirical risk computed by the training data plus a regularization term. So here, J is some penalty function. For example, for ridge regression, it will be L2 norm. And for the lasso, it will be the L1 norm. And the lambda, as we discussed before, so it will be a parameter which can be controlled by the decision maker, and will control the bias and variance trade-off, and in the end of the day, control the expected risk. And usually the higher this lambda is, so the higher bias will suffer, and lower variance, and vice versa. And so now let me try to introduce the following three-stage timeline for this framework, which will be useful concept to define our model. So basically, there will be three stages. The first ex-ante stage, the decision maker will get a training data set, and it needs to pick a learning algorithm. Basically, you can interpret it as it will pick a penalty function, as well as a controlling parameter lambda. And then the estimator will be computed. And in the interim stage, there will come a test data point, but only the feature X will be observed by the decision maker. And then the decision maker can make a prediction using this estimator in the expose stage. So that's all of this very simple framework for static decision theory. So next, I'm ready to present our bias-variance scheme, this model. So here, I will present two versions of it. So one version will be more close to the practice, and we will show that under some canonical assumption, we will observe that, the takeaway message we will observe. But this model is a little bit complicated and not that trackable. Because of that, that will motivate us to consider a more stylized model, which also help us to shed light on this kind of bias-variance trade-off under computation. And we will be more clear in the later of the talk. Cool. Let's first consider the model which will be more close to practice. Let's say we fix a class of available algorithm, or equivalently a class of available estimator. For example, we can interpret that we will fix the penalty function, but we will allow the decision maker to choose this lambda. And so in our game, in our bias-variance game, there will be two players. And each player will obtain an independent training data set. And then they will simultaneously choose this parameter named I, which will control the Bias-Variance trade-off. And we call this the ex-ante version because in this current version, each player will take their action at the ex-ante stage. And then a test data point will be realized, and the utility of the two players will also be realized. And it will share the similar format as our motivating example in the beginning. So we can compute the prediction error for each player on this realized test data point. And the player with a smaller prediction error will get a utility which is a fit 1, which is a fixed reward, minus a prediction error. And the other player will get payoff 0. And let's define the lambda star to be the optimal parameter, which will minimize the mean square error. So basically, this is the optimal lambda star when there is only a single player, which will maximize her expected payoff if there is only a single player. Now, our first theorem says that under some technical assumption, A1 to A5, which I will show you in the next slide. So regardless of what will be the parameter chosen by the opponent J, so the derivative of the player I's utility with respect to her own lambda I will be strictly negative at the point lambda I equals lambda star. This can basically say that regardless of what will be the opponent's lambda J, so deviating to some lambda smaller than lambda star, which is an optimal Bias-Variance trade-off in isolation, will be profitable under competition. And this also suggests that both players playing lambda star, which is the optimal Bias-Variance trade-off in isolation, is no longer a Nash equilibrium under competition. Cool. So here I list the 5 technical assumptions, which I won't walk through here. But so one comment I want to say is that those theorems. So I would say that those assumptions are kind of natural, but also analyzed are kind of restrictive. So it is kind of natural because we can find some learning algorithm which will approximately satisfy those assumptions. And I don't want to. And my interpretation of this first theorem is not saying that you should take this assumption too seriously. But in practice, if you think your problem kind of kind of satisfy those assumptions, it might be reasonable for you to think about if you want to further lower down your parameter lambda, if you think you are under competition. And the final thing I want to note here is that the last assumption, which will be assumption which will relate it to our second model, which will be a more stylized model. Cool. So just to a short summary. So now we have introduced a Bias-Variance game, a quite complicated model, which is close to our statistical decision theory framework. So under some technical assumption, basically what we observe is that by lowering lambda from the lambda star, which is optimal under isolation, will be profitable under competition. But this model is a little bit complicated and not that tractable. And this motivates us to consider a more stylized model, which help also shed the light on this Bias-Variance trade-off. And it's on the other side, because it's more simple, it will enable us to have better characterization and better intuition. And the idea is follow. Suppose that we will fix the test data point. If we fix the test data point, the estimator will basically induce a random variable, which will be a prediction on the label, because we fix the test data point. Or equivalent speaking, you can consider that there will be a distribution of the prediction error, which will denote as A. And what we want to do is to define a Bias-Variance trade-off, Bias-Variance games in the interim version, where two players will select the prediction error distribution directly, assuming that this test data point is fixed. And we call this interim version because the player will take action at the interim stage. In other words, after the realization of the test data point. Again, so this is not practical, but so it will simplify our model a lot, which enable us to have a better characterization. More specifically, let's use H to denote the set of possible prediction error distribution. And then we still have two players, which will simultaneously choose their prediction error, x1, x2. And then so they will realize their prediction error, A1 and A2. And the utility will share a similar format as our previous model. So basically, the player with a smaller prediction error will get a utility which will be 1 minus prediction error square, and the loser will get utility 0. And we see prediction error distribution X is exposed strictly dominant strategy if it achieves higher expected utility among all other possible distribution X prime for all other opponents' prediction error realization AJ. And this is a quite strong solution concept. So the existence of it will imply a uniqueness of a Nash equilibrium, for example. So here is our second result for this more stylized model. Let's suppose that the prediction error distribution will be the normal distribution, where the mu square plus sigma square will equal to 1. And you can interpret this as, suppose there is only a single player, he will be in differences between all the prediction error distribution in this set, because the expectation of a prediction error exactly equals to mu square plus sigma square. Now, suppose we have 2 players under competition. Then the xi with mu I equals to 0 and sigma equals to 1 will be the unique exposed strictly dominant strategy. Furthermore, this utility will be strictly decreasing in the absolute value of mu. And so I want to highlight that. So in our theoretical results, we have 2 simplified assumptions. The first is that we assume that the Bias-Variance trade-off is a constant equals to 1, which equals to the fixed reward in our payoff function. And also, we assume that the prediction error distribution is normal. So in this paper, we also provide additional theoretical and numerical results, which illustrate the robustness of the main theorem. And you can check our paper for more detail. And just to a quick summary. So in this paper, we'll try to understand how the Bias-Variance trade-off will behave under competition. To do so, we introduce these 2 versions of Bias-Variance schemes. One is more complicated, close to the practice, and one is more stylized. And what we observe is that optimal Bias-Variance trade-off in isolation may no longer be optimal under competition. And in general speaking, so bias is more harmful than the variance. In other words, if you acknowledge that you are using a prediction algorithm under competition, it may be more reasonable for you to further tune down your tuning parameter. And that's all for my talk. Thank you for listening.
Questions?
A clarification question. So in your ex-ante formulation, you already proved that for any other like lambda j, it is always good to decrease lambda I. So doesn't that say that the equilibrium is all the lambdas is equal to 0? So like if you have this result, then why do you need the iterative result?
Yeah. So the question is that. So in our first model.
I'm sorry to interfere. Could you just repeat the question for the online audience?
Yes. Yeah. So the question is that. So in our first model, so we show that for any lambda j of the opponent, the derivative is negative. And why? So it seems that this result directly implies that playing the lowest bias is a dominant strategy equilibrium. So this is a question. So here I want to make a clarification that our first result is saying that the derivative is negative at the point when I am using the lambda I equals to lambda star. So the result is saying that regardless of what opponents use, but I'm profitable to deviate from lambda star to smaller.
And lambda star is the optimal under 1 player?
Under 1 player.
This might not be directly related to your model, but how would introducing more competition change your results? Like, for example, you currently model utility as 1 minus, the error squared. But say that you have more than 2 people choosing, and then would that still and you sort of study a oligopolistic model instead of the one for all, or all or nothing. So how would that change? I'm just curious.
That's a good question. So the question is that. So how the results will change if we have more than 2 players. And so for our stylized model, so our results is saying that, so regardless of what's the prediction error of the opponent, so the utility of this player is monotone decreasing as he decreases his bias. And this directly implies that, so this result also holds for more than 2 players. But for our first model, which is more practical, So here, we do not have a good characterization beyond 2-player. And I want to thank for the organizer.
Let's also thank all the speakers and see you all tomorrow.